In this case, the calculation was done at an isolated cluster level. They did not take into account the band structure effects and some very important interaction effects accurately. It turns out that if you do that, then another interesting phase that forms, that in this limit, where you begin to form a metal, but this PD hopping interaction actually splits, pushing this state up and pushing these plates down in a bonding antibonding like structure, opens up a gap for up to some values of delta, which normally would have led to a metal formation. So basically the insulating phase extends. This part they thought is the one where the metal forms, but actually this phase line shifts significantly in this direction, where you have a delta much less than delta critical, and yet a gap forms, and that gap forms neither because of delta, because delta tells you that it's less than delta critical, so it should be metallic, nor because of U, because U is irrelevant because it's much larger, but because of a bonding antibonding interaction, which means hopping is the driving force for forming the gap. And that happens in a limit that we had termed covalent insulator, and now popularly known as the negative delta insulator. And this, we actually originated this, and because of which the phase diagram, where earlier people thought this delta equal to 0 would be the phase line of metal insulator, turns out that you can go into a negative delta state and yet get an insulating phase. And this phase is very important to describe all the nickelates, the cuprates, the late transition metal oxides, because that's where you find this negative delta insulators. And they have very peculiar properties arising from this negative delta behavior, and yet an insulating range. Having told you that this modified ZSA diagram, and told you that this phase diagram will explain everything, then I must be able to go back and take the first slide that I told you to motivate you and say that transition metal oxides show non-monotonic behavior. Remember, lanthanum titanate was almost a metal, a very small band gap insulator. Then it became lanthanum vanadate, gap insulator. The gap kept increasing, then kept decreasing, and lanthanum nickelate became a metal. Why does it happen? The reason that happens is that, okay, negative delta insulator I've already talked about. This phase diagram also claims that the insulating phase that you get everywhere is an antiferromagnetic insulator, and the metal that forms all over is essentially a paramagnetic metal, except for the fact that we also found evidence for a thin sliver of antiferromagnetic metal that formed just across the phase line. But let's not worry about that right now. Let's get back to the non-monotonic behavior that we are talking about. I'm going to ignore spin altogether. As I said, magnetism I'll not get into. And the spin is implicitly taken into account when you're doing your housekeeping or accounting of hopping. Right? That's implicitly taken into account. So basically it will go into modifying the W so that it obeys the spin correctly. At the tight binding level, I just have to keep a sigma as a label, that's all, and there's nothing else. And Coulomb interaction.
You said about paramagnetic metal, that's why.
But in the calculations, we have the spin. In the calculations, I have the spin. Right now, I'm not referring back to the spin because, as I said, that magnetism is something that I'll not get into in a big way. But in all the calculations, spin is rigorously taken. Okay, so this non-monotonic behavior that I talked about, how do I understand? Now, let us try to understand it by looking at it and saying, going from titanium to nickel, what am I changing? In fact, I already had told you that the 3D level contracts because the nuclear charge is increasing, right? Going from titanium to nickel. Also, the D level is getting more and more stabilized, naturally, getting pulled down. So, as 3D level energy comes down, then it must become easier to transfer an electron from oxygen to the transition metal. Because at titanium, the D level was up there, oxygen was here. I go vanadium, chromium, manganese, iron, cobalt, nickel, copper. So I'm coming down. So the energy required must be going down as I go across. So delta decreases as I go from titanium to nickel. So two things are happening. It's not one thing. And as soon as two things are happening, two monotonic functions can be combined to give me a non-monotonic behavior. Correct? And that is precisely what is happening. Now, remember, as I go from titanium to nickel, U increases, delta decreases because we are going to put it on the phase diagram. The phase diagram is here, and then I start from here, titanium, delta is large because titanium early, but Coulomb interaction is small. So I start from here, and as I am going towards nickel, my Coulomb interaction is increasing and delta is decreasing. That means I am moving back. And so I start from very close to the phase line, so I have a very small gap. Gap begins to increase as I go further away from the phase line, and then begins to decrease and becomes metal because I go across the phase line. Simply because that the character changes from here, which is the Mott-Hubbard insulator, through a negative delta insulator, it becomes a PD metal. And that's the origin of the non-monotonic behavior that I told you about right at the beginning. Is this clear now? Why we get a non-monotonic behavior by combining two monotonic properties of U changing and delta changing across the period. So this is the way you'll be able to understand when you look at different kind of transition metal compounds, and not only oxides.
Has that have to do anything with the atomic radii?
Atomic radii, the U increasing is the atomic contraction. Because as you go from titanium to nickel, you know that the atomic size decreases, which is equivalent to saying that the 3D orbital is contracting, and when 3D orbital is contracting, you are squeezing the electrons to overlap with each other more, so the Coulombic interaction is going up. So the U strength actually is increasing. So going from titanium to nickel, U is increasing, and delta is decreasing, so you're going from here to there.
What role this lanthanum plays? Lanthanum has no one.
Lanthanum has secondary role. Lanthanum is to stabilize the structure. There are subtle effects that can happen. I'm not going into those as of now, because you can do a lot of gain by changing lanthanum, keeping the transition element the same. Because then what happens is that lanthanum, you can take the lanthanide series. So you can lanthanum, cerium often doesn't work. Praseodymium, neodymium, you can go right across gadolinium, all the way up to lutetium and yttrium, and the size is decreasing. So size is decreasing, so what it does is to try to bring the transition metals closer together. But it cannot bring it closer together because of the bond lengths as such that it wouldn't allow it to contract. Then these octahedra are tipped. And in fact, the bandwidth changes. Titanium-oxygen, titanium bond angle decreases from 180 degrees. These are details, but since you're an expert, I'm telling you. So the bandwidth will decrease. So that's a way of changing the bandwidth. So it's an indirect effect. It allows you to play with the structure, distance, and angle to change the T. And that game is played a lot. I mean, in the context of the manganite, it has been hugely used. Titanate, some amount in the cuprates, in neodymium cuprate and lanthanum cuprate behave very differently. So all these, and lanthanides, for example, lanthanum nickelate is metal. All the other nickelates, neodymium nickelate shows a metal insulator transition. It's starting from metallic state, it gets into insulating state. And that temperature systematically changes as you go to smaller and smaller. It happens simply because nickel oxygen, these octahedra tilt as you put into smaller ones, and therefore the bandwidth decreases. So it gets more strongly correlated. So it, starting from being inside the metallic state, it comes out into this covalent insulator, the negative delta insulator state. Neodymium nickelate and other nickelates actually are examples of this negative delta insulator. Yes?
Why delta is decreasing is not clear to me.
Pardon?
Delta is decreasing, increasing this.
It's not clear. Okay, it's very simple to understand. If you do you remember the hydrogenic solution? Hydrogenic energy, if you look up, it has a Z in the expression. Energy. Z is the atomic number, right? And at the hydrogenic state level, you'd find, just look at that expression, right? So the En is equal to minus something, I think it is a Z square, I don't remember who's taught. I think it is most likely to be z squared as well. E squared, yeah, over n squared something. Yeah. And by n squared something. So n is the same because we're talking about the same quantum number state. And there's a minus. So as increase z, you can see how quickly your state, this negative energy is becoming more and more negative energy. It doesn't happen that fast because of Coulomb interaction is there. But essentially what one is saying that the nuclear charge is increasing, the attractive charge is increasing. So the energy is coming down.
Actually, that is also Coulomb, but it's a nuclear.
Yeah, it's an attractive Coulomb interaction, but you're paying another Coulomb interaction, which is also you're putting in that many number of extra electrons. Every time I'm saying that Z increasing, I'm cheating you a little because I'm not telling you that I have to put in the same number of electrons. So the effective charge going up is not as much. Okay? So it doesn't go down by as you'd think by look at minus Z squared dependence, but it keeps going down. And the D level coming down means delta is decreasing because oxygen remains at the same place and this is coming down. You can see that delta. Then I'll now show you that actually while this is a very good generic picture and based on this you can answer quite a lot, but many details would change drastically if you bring in other aspects. For example, this was calculated for some particular situation. Now let us go and that was actually for D9 case. Taking Q-pret as the basis. Those are details that are unimportant because these are generic features, true. But to give you an appreciation for what can happen, we move out from D9 and do the calculation for D8. So the equivalent, if that was Q-pret, it is the negative. Then if I take the Hund's coupling strength equal to 0, now you see that D9, I didn't have to ask about the Hund's coupling strength. There was only one hole because there can be 10 electrons. So there was only one hole per side. So it didn't matter what the Hund's coupling strength is, which measures between two parallel spin and an anti-parallel spin, what is the energy difference. There's only one spin at each side. Okay? But if I take D8, then of course I have the possibility of having these two holes in parallel and anti-parallel configurations, and they would have very different energies, and I need to keep track of it. When I keep track of that, if I first say J equal to 0, that there is no difference between the two energies, so it's sort of equivalent to the D9 case, I get a phase line exactly like I got before. This is a phase line. Everything on this side is insulator, everything on this side is a paramagnetic metal, everything on this side is a paramagnetic insulator. It's paramagnetic simply because I have not distinguished the energy between this and this. But now make J a finite value. A typical value will be J equal to 1 in the order of, if you are talking about 3D level. And as you take J equal to 1, then the phase diagram looks different. This is the, again, this is U delta phase, it again looks like this. That's a generic, very robust conclusion that in this part, U and delta both are large and you'll get an insulator. Below it, you'll get a metal. But then there are other things. First of all, this phase transition becomes a first order transition, unlike in the previous case, which is a second order transition. And there's an antiferromagnetic metallic phase that can form, and then there is a reentrant transition possible. There's a paramagnetic metal. There's a phase where U equal to 0, and yet you can get a insulator, which is called a Slater insulator, merely because of formation of an antiferromagnetic insulating state. It's just the antiferromagnetism that gives you an insulating state, which is called a Slater insulator, etc. So there are subtle changes that can happen. The only reason I'm showing you, you don't have to remember this. Remember that sometimes details matter. Depending on what you want to understand, you have to think of the details also and not get stuck only with the generic feature that I have told you. Start with understanding from the generic understanding. Then when you find that there's certain things that are contradicting, your observation is contradicting your understanding, then you know that now is the time to move on to the details and ask finer questions, as was asked over here. So, Okay, now before we go on, I will talk about, without actually going into detail, but a whole lot of materials, chemistry and physics is done, not only just this LaMO3-like compounds, which are all very nice and clean and has no defect, etc., so to speak, but when you take this lanthanum and put something else in place of lanthanum, and in fact what you could be doing is very nasty, is that lanthanum, which is a trivalent ion, that means it donates 3 electrons to the rest of the system, you replace it with something that donates only 2 electrons. That means that system needed 3 electrons, but you denied it some electron, which means you are doping the system with holes equivalent. So you can put strontium in place of lanthanum and make substitution such that that hole would either go to the metal site, increase its valency, because eventually it has to be charge neutral, or it has to go to the oxygen site and change its valency. Or it would be somewhere in between the two, and the question is one has to understand where does it happen and how does it happen. To understand with respect to the generic pictorial representation that you have had of this whole doping, starting with a Mott-Hubbard insulator, I'm not going to dope up metal, because doping a metal is going to be boring, and you'll know in a moment why. But Mott-Hubbard insulator is this one. If I put holes in that, all that would happen is that some electrons get removed. You see that becomes a metal immediately. If I take a charge transfer insulator and I put a holes, it becomes metallic again. Here the holes went to the transition metal site. Here the holes went to the oxygen site. So the character of the metallic states will be very different, and that's what is actually implied here. That here the holes went to the metallic side, here the holes went to the oxygen side. Of course, it's never pure oxygen side or pure metal side, because there is always hopping and the character gets mixed. The question is, dominant character, is it oxygen type or metal type? And you can immediately see that in the case of the Mott-Hubbard type, the holes will be in the D level. In the charge transfer type, the holes will be in the oxygen D level. To make it matter.
Just complicated is that you split the D band, but not the P band. Is it because there the U is less?
I had spent a lot of time actually showing that. You were sleeping at that time. I noticed. I had defined U to be equal to 0 in the P band. I had also described to them that there is a way of actually considering, and I said I'll come back to that, if U is not 0 for the P band, it can also renormalize. There's a way to renormalize and take its effect in the D band U and continue with the U equal to 0. That's the reason we don't take that. And P being a filled band,